Hi everybody, welcome to our first lecture. It's on chapter 2, straight line motion. So before we start, we're going to make a little distinction here between kinematics and kinetics. Kinematics is where things are, where objects are, when they are in certain locations, and what they are doing. No forces. We're not concerned with any forces. We're just looking at the relationships between these things. Where, when, and what. Kinetics here is where we deal into the effect of forces and the relationship between forces and subsequent motion. Okay, now one other thing that we have to get straight is the definition of a particle. A particle is a relative term. An airplane is not a particle if it's on a runway and you're getting on it, or it's being towed by a vehicle or something like that. It clearly has different parts that are going to react differently to the forces put on it. But as it's flying through the air, in terms of considering its velocity, its acceleration, and that sort of thing, we can consider it a particle. So, particle is sort of a particle test. If you can describe it as a point like mass with infinitesimal size. Now, obviously, a plane does not have infinitesimal size, but it does compared to the size of its path. Okay, so really, if the particle is small, a working definition is if the particle is small relative to the size of the path, we can call it a particle. All right. So the first concept is displacement. Displacement. So change in place. This is opposite or not, or something, like a negation, and placement. So you're changing the placement is a way to think about that. So it is a change in position. All right, it has dimensions of length. And we often do, we try to put dimensions when we just want dimensions. We use brackets to signify that. And it's a change. It's a change in position. So change is, in Greek letters, is signified by the letter delta. So delta x, the change in the x position, is defined, this is a definition, equal to the final position minus the initial position. So an x with a subscript f, an x with a subscript I. All right, so that's its change in position. That's its displacement. Okay, now, notice that this is different than distance traveled. All right? Displacement is not equal to distance traveled. As a rule. Certainly it could be, but as a rule it's not. For example, if you take a baseball diamond, here's home plate, first base, second base, third base, home plate. All right, so there's a hit. It's a home run. The runner goes here, 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 and here. On each leg here, 90 feet. What's the distance traveled? The distance traveled equals 4 times 90, or 360 feet. But the displacement is just the final location minus the initial location. Started at home plate, ended at home plate. So XF and XI are the same, so that means delta X equals 0, since the final position and the initial position are the same. All right, so just one more note here. Straight line motion means one dimension. So like along a number line. Okay, so for now we're dealing with one-dimensional motion. All right, so let me make some space here. So getting back to our expression for displacement. It's defined as final minus initial. Okay, so this delta X is positive if the final is greater than the initial displacement, and displacement is negative if the final is smaller than the initial displacement. Okay, so this kind of brings in the idea of vectors, which we're going to deal with a lot more in the next chapter. But as a quick introduction, you can compare two quantities, scalar and vector. A scalar quantity has a magnitude, and it may have units, usually has units. Once in a while you have pure numbers. Vectors have magnitude, units, and direction. All right, and they're often they're signified like if the scalar is A, the vector would be A with an arrow or a bar over it. Might in your book they use boldface print. Different ways, different situations do it differently. So just be aware of it. Now, in one dimension, vectors only have two directions. In one dimension, you can only go this way or this way if you have some origin. So you call one direction positive and one direction negative. So in one-dimensional vectors, you just have a positive direction and a negative direction. All right, so let's mess with this a little bit. So we have a particle. Moving along a straight line. Let's see. At t0, it is at point x0. At t1, it is at x1, and so on. All right, so we're going to draw our coordinate system, which in one dimension is just a number line. And we've got 0 here. So we're going to represent these positions with vectors. So here's 3 that we're going to represent. x1 is a positive 2.0 meters. x2 is a positive 5.5 meters. And x3 is a minus 2.5 meters. Okay, so I'm going to make 1, 2, 3. So minus 1, minus 2, minus 3. In the other direction, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 5, 6, 7. Okay. So, to represent these vectors, okay, this is x1. Starts at the origin and goes 2 meters in the positive direction. x2 starts at the origin and goes 5.5 meters. x3 starts at the origin and goes 2.5 meters in the negative direction. All right, so now consider the change in displacement. All right, so we're going to look at changes in displacement. Those were displacement vectors. Change in displacement is going to be key in our next quantity, velocity. So, a change in displacement. Remember, displacement was a change in position. Now we're looking at the change of that change, right? So, the change in displacement is defined as x2 minus x1. And in general, well, actually, not good to use 2 and 1. Let's generalize that. An xb minus an xa. So whatever the latter displacement minus the initial displacement. All right, so if we were to apply that to here, delta x, the initial change in displacement, right, is going to equal x1, this is a vector, minus 0. The displacement at 1 minus the displacement at 0 time. x1 is 2. x0, we were at the origin, so it's 0. So that equals positive 2.0 meters. Delta x1 is the next one out. That's going to be x2 minus x1. x2 was 5.5 minus 2.0. So that equals 3.5 meters. So let's put that on our number line there. Okay, so this right here is x2 minus x1, or delta x1. All right, it has a magnitude of 3.5. You can see that, 5.5 minus 2, and it's in a positive direction. Okay, delta x2. Same pattern, right? x3 minus x2, x3 minus 2.5 minus 5.5 equals minus 8 meters. So this one, minus 8 meters long. Okay, so that is x3 minus x2. So that's going to go from 5.5 to negative 2.5. This is delta x2. All right, and now lastly, delta x3, I'm going to define as this one, x3 minus x1. You can do any ones you want. If you had 4 or 5 of them here, you can have change in displacements between any of them, and you can subscript them anything you want. All right, just be clear with your definitions. x3 is minus 2.5 minus x1 is 2.0. This is a minus 4.5. All right, so that's x3. x3 is going that way. Then a minus x1 turns around, right? A negative vector is the opposite direction, so that's going to be here, delta x3. Okay. So that's displacement. That's change in displacement. And we're going to leave it there for now. Let that sink in, come up with questions, and I'll see you on the next video where we're going to talk about velocity. All right, see you later.